Welcome! In this lesson, we derive the three equations of motion used in one-dimensional kinematics. We begin with the first equation of motion. This equation relates final velocity, initial velocity, acceleration, and time. Before we derive the equations of motion, let's define our standard variables. U for initial velocity, v for final velocity, A for acceleration, s for displacement, and t for time. Acceleration is defined as change in velocity divided by time. Expanding change in velocity gives final velocity minus initial velocity. Replacing words with symbols gives a compact mathematical form. Multiply both sides by time. Add initial velocity to both sides. Rearranging gives the first equation of motion. Final velocity equals initial velocity plus acceleration into time. Now let us derive the second equation of motion. This equation relates displacement, acceleration, initial velocity, and time. Displacement equals average velocity multiplied by time. Substituting the expression for average velocity. From the first equation, replace final velocity with u+at. Simplify the numerator and rearrange terms. Distribute the multiplication over the two terms. Cancel common factors and simplify. This gives the second equation of motion. Displacement equals initial velocity multiplied by time plus 1/2 acceleration multiplied by time squared. Finally, we derive the third equation of motion. This equation connects velocity, displacement, and acceleration without involving time. We again begin with displacement equals average velocity into time. Replace average velocity using the known expression. Replace time using the first equation of motion. Rearranging gives a product of two binomials. Apply the identity a plus b multiplied by a minus b equals a squared minus b squared. Multiply both sides by 2a. Move u squared to the left side. Rearranging gives the third equation of motion. Final velocity squared equals initial velocity squared plus 2 times acceleration multiplied by displacement. Now that we have successfully derived the three fundamental equations of motion, let's explore how they transform when an object moves under the sole influence of gravity. We will look at two specific scenarios side by side, an object in free fall and an object thrown vertically upward. When an object is in free fall, acceleration points downward in the direction of motion, so we replace A with positive g and displacement s with height h. Conversely, when a ball is thrown upward, it moves against gravity, meaning its acceleration is negative g. From these equations, we discover several critical rules. First, if a ball is dropped from rest, its initial velocity is 0, simplifying our displacement equation. Second, neglecting air resistance, the time taken for the ball to reach its maximum height is exactly equal to the time it takes to come back down. Third, the speed of the ball when it returns to the ground is identical to the speed it was thrown with, though its vector direction is reversed. And finally, at its highest peak, the ball momentarily stops moving before falling down, meaning its final velocity at maximum height is always 0. We have now explored the core equations of motion, customized them for gravity, and uncovered essential properties governing vertical projectile paths. Recognizing these underlying symmetries and key boundary values makes analyzing real-world physics intuitive. Thank you for watching and keep exploring physics.